In this video, what I want to do with you is actually bring some of the concepts that we have been talking about throughout chapters 6, 7, and 8 and bring them together. And I hate to use that long word that may make you cringe. Yeah, stoichiometry. It is like a bad rash. It's a gift that keeps on giving. Now, I hope you don't treat stoichiometry as a bad rash. I hope it kind of grows on you like athlete's foot a bit. So I thought what I would do is actually go through a chemical reaction that we used to use a lot in black and white photography. Now, you guys are young, and I know we can make black and white photographs in our photography department using digital means, but in the old days, we used to make black and white photography using good old chemistry. So I actually looked up some baby pictures, and I'm willing to share with you. Turns out I was actually a much better looking baby than I am an adult. When you look at that, that's actually had a little more hair in those days as well. It was pretty typical to have black and white pictures 50 years ago or more. So your grandparents, even maybe your parents, if they're fossils like me, had black and white baby pictures. So here is the chemistry behind black and white photography, and I'm going to go through some Stoic with you. Good news is you've learned everything that I'm about to go through. That's why I mentioned to you before that the hardest stuff is kind of behind us, I hope. So let's take a look at the reaction involved used to make black and white photography. This is in section 9.5 in the Nelson textbook, and this question here sort of gets into what volume or how many milliliters of a dilute solution of sodium bromide, in this case 0.125 molar sodium bromide, completely reacts with 25 milliliters of 0.115 moles per liter silver nitrate. So just like before, we have our equation. Yes, it is a double displacement. Silver nitrate reacts with sodium bromide to make silver bromide and sodium nitrate. We don't really need to worry about products, ironically, in this question. So while we know sodium bromide is a precipitate, the question actually focuses on reactants only. In addition to that, I just placed our 2 mole triangles along the side because we have to use both of them today, as I just mentioned. Well, in the experiment, we write down what we know. We know the concentration of the silver nitrate is 0.115 moles per liter. And we know the volume of the silver nitrate is 25 mils or 0.025 liters. We're going to convert to liters because our units work out better that way. We know the concentration of the sodium bromide is 0.125 molar, but we don't know the volume. That's the original question, so I will call that X. Well, we have to use the most recent mole triangle first because we have concentration and we have volume. We can find moles. Remember, moles is N, and N is the only thing that actually appears in both triangles. Not surprising, because the mole is the central concept in chemistry. So moles is C times V. We go through the math. 0.115 moles per liter times 0.025 liters. Remember to cancel out your units. We get a very small number, and I'm not going to round off until we're finished the problem, otherwise we get a round off error. And as I said before, if you're the engineer building the bridges that we drive on and you round off, the bridge falls down. So 0.002875 moles. That's what our calculator tells us. This question is nice because these reactants react in a ratio of 1 to 1. There is no coefficient to deal with. It's just a 1 to 1 ratio. So the moles of the silver nitrate in this case are identical to the moles of sodium bromide. That's why I wrote that down here. And we get to use our mole triangle again, this time to find the volume of the NABR, because we now have moles and we had concentration originally. So V is N over C. We plug it in, our 0.002875, the number under the calculator, divided by 0.125 gives us 0.023 liters. Now, 0.023 liters doesn't mean a lot to most people. We in the lab typically convert to milliliters because we can envision a milliliter amount. So divide that by 1,000 and we get 23.0 mils. Notice we can carry 3 significant digits in our answer because our problem has values that are reported to 3 sig digs, which means the equipment we used was somewhat accurate. That's our answer for A. Part B goes back to the good old Stoic of yesteryear in chapter 7. It says how many grams of sodium bromide react? Well, we have the volume, and we have the molarity, and we have the moles. So we can go back to our very original mole triangle, way back to mole land, and find the grams of NaBr. Because you already knew from before that grams equals moles times molar mass. We just found the moles of NaBr, 0.002875, and we can look up the molar mass quite easily for NaBr. I've rounded it a bit, not too much, it's 103 grams per mole. And our units cancel like normal, and we get about 0.296 grams. Okay? So a little bit less than 0.3 grams. So there you have it. Very simply, we can add 2 solutions together into a test tube or a beaker or what have you. We could precipitate out the product if we were to look at products, but in this case, we're just simply looking at reactants. Very beautiful way to bring the stoichiometry concept that you learned before together with solutions. And I hope this helped. We'll do a little bit more of this to give you some practice, maybe in an example where the reactants do not react in a perfectly 1-to-1 ratio.